So I'd like to talk to you today about some of my work on 3D printing for synthetic chemistry and medical applications. If you want to find out more about this, you can follow my Twitter and Instagram account where a lot of the pictures and concepts are shown from this talk today. So a lot of research in my group has traditionally focused on medicinal chemistry, looking at anti-cancer drug discovery, antiviral drug discovery, and neuroscience drug discovery, particularly looking for molecules that enhance memory. And some papers we published a while back on this one. But more recently, our research has focused on 3D printing, and this has spread across a wide number of areas, ranging from 3D printing and catalysis, where we have modified stirrer beads, which normally mix reactions, to make the mixing far more efficient and actually use the stirrer beads themselves as catalysts. What I'll be talking about in more detail today is continuous flow chemistry, where we developed a new continuous flow reactor. This will then lead on to virtual reality and some of the work we've done more latterly. Other research in the group focuses on reactive extrusion, where we're making polymers with drugs that are incorporated. We also look at point-of-care diagnostics, where your phone is actually a point-of-care device for analyzing patients. We also look at 3D printing with drug delivery, where we try and develop and design devices that can release drugs for sustained release, and also 3D printing and personalized therapies, where we develop 3D printing approaches to wound healing for patients. But moving back towards chemical synthesis, in most chemical synthesis concepts, we look at the mixing of two reagents to make a product. So we take reagent A, we react it with reagent B under various conditions depending on heat, time, light, electrochemistry. We use them to form a product C. Now, normally you can view this as a round bottom flask, where here we have a round bottom flask with a magnetic follower inside, where reagents A and B are mixed to give a product C. And this reaction is required to be carried out in flasks, but often leads to poor mixing of reagents. And for larger flasks, you need larger amounts of material. There's safety risks of exotherms with this approach, and risks of byproduct formation. And one of the other challenges with this, there's a difficult reproducibility in this process in terms of the scale up. So how does that work? Well, this video starkly illustrates this. When we mix two reagents A plus B and stir these with a magnetic follower, you can see very clearly that there isn't very much mixing throughout the entire flask. So for about a minute, these two reagents aren't mixing very well in the flask. You have a central column for high concentration, followed by an outer volume of a low concentration. Now what this means is you can get byproduct formation in this process, or exotherms, or unwanted reactions. So carrying out chemistry is quite often difficult in terms of the scale up. When we think about why this is the case is, well, when we carry out a reaction, quite often the reaction is fast, but because the mixing is not efficient, quite often the products are formed in part of the mixture while starter materials still remain in there. So after about 16 hours of a reaction, what you will find is that some of the starting materials have converted through to products, while some starting material still remains. After a period of time, once the reaction is complete, all of the starting materials have been converted through to the product. But quite often in chemistry is that if you carry on heating some of the reagents or from products, they will degrade. So batch chemistry isn't that efficient. And so that's why a lot of chemists have moved towards flow chemistry. This is where we take two reagents, A plus B, we pass them through some very narrow tubing, where we have a residence time where reactions can be heated. This passes out to the product C. And now scale up this is quite different. If we want to make 2 mils of product, we just simply mix 2 mils of A plus B to get the product. This is the only point they come into contact, and this is the only point at which they're heating. And so in flow chemistry, we are looking at very small volumes of material mixing at any one time. So we don't have the same problems that we have within batch. So how does this work? Well, if we have a reservoir of A plus B, small amounts of that go into a column where the reaction is heated, product is then formed, and this then passes out the other side. And so in a continuous process, what is happening is that as we pump more and more through this channel, you can view the product coming out the other side and more starting material coming in to replace it, depending on how much is needed to be made. So it's a really great way of carrying out chemical synthesis, because we can easily pump reagents through a small tube and get products out the other side, becoming reproducible. So in terms of flow chemistry, it's very good because we have fast mixing. We have very efficient heat transfer because you only have very small volumes. We have control of residence time. We have increased safety. And it's enabling technology because we can modify it and match the suit. And it's very easy, as I mentioned, to scale up synthesis. So it lends itself very ideally for 3D printing. And you can see here one of our early prototypes, which we 3D printed for a column reactor for this type of approach. But one of the challenges with flow chemistry as it currently stands is it's very expensive. It's normally about 14 to 90,000 per system to purchase one of these materials, one of these flow reactors, meaning that most labs don't have access to this equipment. Another challenge is that in a laboratory where you want to use your fume hoods to maximize their utility, if you have flow reactors, they tend to block fume hoods, and you can't do anything else while you're using them. What you really want is a flexible fume hood space where you can do everything you need within the same fume hood. Now, in order to try and overcome this barrier, what we wanted to do was to try and develop an entirely new flow chemistry system, one that would be very simple to run, low cost and effective, but also small footprint. Because when you think about a flow reactor, you have a solvent reservoir where you inject your reagents, or alternatively have reagent injection at this place either side, so A plus B over here. We have flow control, so 2 pumps which control the flow rates, i.e. the speed that A plus B move through the tubes. We have heating and residence time, and then the product comes out the other side. What we wanted to do was try and build an entirely new flow system around a stirrer hot plate. What we thought about was this approach, where we have a solvent reservoir, we have a point for reagent injection, we have flow control, and we have heating and residence time. So this was our concept where we came to with 3D printing, where we could redesign an entire new flow system built around this concept, a small, low footprint. The idea behind this was that this system would be run rather than via pumps, via compressed air. So compressed air would come into the bottle, force the solvent out through the tubes into these reagent injection points, where we can then add in the 2 reagents and get the product out at the other end. The residence time would be controlled by the number of reactors we have at the bottom, which should also be 3D printed, giving us a real good ability to control heating and residence time, but also in a very simple and small footprint system. So going back to 3D printing, a lot of time it's rapid prototyping as well. As you can see here, the very easy or early prototype we developed, full of tubes, complete disaster in terms of its layout. But it just goes to show you what you can design if you want to using 3D printing. We built a holder for the injection, tubing that was a bit of a disaster with the connection, but also the flow control and the valves shown below. But it's very easy to quickly have a concept and an idea and to develop a prototype in 2 days, just on a very simple idea, a thought experiment. In terms of the reactors, so the residence time, we decided to print in polypropylene, where chemicals can come into these disc reactors shown here. And by increasing the number of disc reactors, we can increase the residence time in terms of the flow rate through them to get the products out the other side. And we can easily match and modify the flow path depending on what is required. So here we see the advanced system. So it's a very small footprint, fits quite nicely onto a stirrer hot plate, but it's much smaller than the commercial system. It runs up to about 20 psi in terms of glass or polypropylene disc reactors, and between 0.1 mils per minute and 8 mils per minute flow rate. So quite a simple approach in terms of what you want to do. One of the neat things about this, you can see its size. It's small and adaptable for most fume hood usage. Flow rates are easily predictable by these restricted devices which we place at the end of the flow path, and so we can easily select the flow rates that we want. Chemistry is pretty straightforward, again, some of the publications you saw earlier, but you can see how the reaction proceeds. Here's where the reagents come into the reaction. We've taken this snapshot photo where the reaction is now passing through these 2 reactors. It's going from one reactor to another. So here we see the front end, where it's moving through this next reactor. And here we see the tail end. So it's a bit like a bell-shaped curve as it passes through the flow reactor. But you can easily make the products very simply in this manner. So what we've shown with this is we can easily modify the path length and the flow path by changing the reactors. We can alter the residence time by the number of the reactors or the flow rates. And we can have multiple flow reactors in any one fume hood with this approach. So again, this is the power of 3D printing. You have an idea, you develop a prototype, and you can take it through to almost semi-commercial utility. We can modify it to suit as well. So here's the electrochemistry variant, where now rather than doing heating and residence time, we're using electrochemistry to carry out a chemical reaction. And this also works very well. One thing we also wanted to do was develop a portable system, and you can see here the actual sort of concept and the packing that we designed around this. So it's a very simple system for chemical synthesis. Now, we've just finished the final development of this, and so here you can see the actual commercial system that will be launched in January. So this was 2 years from concept with 3D printing to launch, and it still has partly the parts behind 3D printing with this. We still have the 3D printed reactors because they're simple and easy to produce, so low-cost manufacturing. And also parts of the system are also 3D printed as well. So the top and the bottom are 3D printed, meaning that we can easily modify and match to customer requirements. But it just goes to show how 3D printing is so powerful for taking a product through from a concept as a prototype all the way through to a commercial product in 2 years from idea through to customer launch. We've also got software around this as well, using the Arduino platform and some robotics as well. I won't go too much into this, but we now have a system we can control remotely via Ethernet or locally and control the residence time, flow rates, and monitor the temperature and track as well. But very briefly before the end, what I want to come back through is about 3D printing. Is its digital concept. 3D printing is all about taking digital designs and producing physical objects. But these digital objects don't necessarily need to be physical. We've also been looking at virtual reality in this approach. And one of the things about lockdowns that pushed us forward on this was that in reality, we can't have physical interaction with students. But in virtual reality, we can effectively. We can be in the same room as students. We can show them physical objects, virtual objects, in VR. So how did this work? Well, using a VR headset, we can easily now meet students in a meeting room that we create in virtual reality. We can take our physical objects that were 3D printed and just take the digital data and use these to teach students in exactly the same manner as we would do in a meeting room. And so here you can see the virtual reality room shown here and the real meeting room shown below. So we've deliberately developed this concept where the chairs are out of alignment so they match the current arrangement in a normal meeting room. So most people when they're in the VR environment will feel as though they're in exactly the same environment. The laboratory is also replicated. So here we have our lab. 18th of March, where we started the lockdown, we created a VR prototype. And here you can see the flow reaction in the system here. So it's a very quick way to take digital data and create a virtual reality environment that can be used for education, but also for teaching and ultimately research in the long term. So this is the journey about 3D printing. It's not so much about making objects, it's about using your imagination to create digital data that can be used to create physical objects. And I'd like to sort of hope that we've shown you quite a nice story about 3D printing and its circular role to come back through to the digital concept and digital designs, but ultimately how you develop material and take it through to market. But I couldn't have done any of this without all of these wonderful people here. And I'd really like to sort of point out Dr. Matthew Penny, Dr. Zaid Moafak, Dr. Nobia Rao, Zijing Zhao, and everyone else here for all the hard work they've done developing this concept. And finally, thank you for listening.